We're about to build cities on the moon, not in some distant science fiction future, but within the next decade. And the timeline is moving faster than most people realize. Right now, two superpowers are racing to plant permanent boots on lunar soil. NASA's pledging to land astronauts before 2028. China's targeting 2030. Both nations are pouring billions into infrastructure that'll turn the moon from a destination into an address. But here's what nobody's talking about. The engineers building this future are wrestling with problems that make rocket science look straightforward. You can't just pack up some habitats and call it a colony. The moon is trying to kill you in ways Earth never prepared you for. Radiation that'll shred your DNA, temperature swings of 280 degrees Celsius, dust so abrasive it can saw through Kevlar, and a vacuum so complete that your blood would literally boil if your suit failed. Yet we're doing it anyway. Because the first nation to crack lunar colonization doesn't just win bragging rights, they control the gateway to the solar system. Let me show you what it actually takes to build a city on another world. The race officially restarted in 2017 when President Trump signed Space Policy Directive 1, ordering NASA to return humans to the moon. Not for a few days of flag planting like Apollo, for permanent occupation. The Artemis program emerged from that directive with a mandate that would have seemed impossible a generation ago. Establish a sustained human presence on the lunar surface by the end of this decade. NASA's current timeline puts Artemis 2, a crewed lunar flyby, no earlier than April 2026. 4 astronauts will loop around the moon in a 10-day mission that tests life support systems and radiation shielding. Artemis 3 was supposed to land humans on the surface in 2025. That's been pushed to Artemis 4 in early 2028. But here's where it gets interesting. After those initial landings, NASA isn't planning occasional visits. They're targeting landings every 6 months, then every few months, building toward a permanent base near the lunar South Pole with a price tag of $20 billion over 7 years. The political pressure is intense. NASA Administrator Jared Isaacman stated publicly that American astronauts will walk on the moon before the end of Trump's current term. The clock is running in this great power competition, he said, and success or failure will be measured in months, not years. That kind of language signals something crucial. This isn't just about exploration anymore. It's about territorial presence. Meanwhile, China's been quietly building the infrastructure for their own lunar ambitions. They landed Chang'e 4 on the far side of the moon in 2019, the first soft landing anyone's ever achieved there. Chang'e 5 returned lunar samples to Earth in 2020. Chang'e 7 and 8, scheduled for 2026 through 2028, will scout water ice deposits and test construction technologies. Their timeline for putting astronauts on the surface? 2030. Using the Mengzhou crewed spacecraft and Lanyu lunar lander, 2 Chinese astronauts will touch down somewhere near the South Pole. But China's thinking bigger than a couple of flags and footprints. They've launched the International Lunar Research Station project, a scientific facility that'll span the lunar surface, lunar orbit, and Earth. Basic model by 2035, extended version by 2050. 17 countries and over 50 research institutions have already signed on. You might wonder why everyone's suddenly obsessed with the moon after ignoring it for half a century. The answer comes down to one substance: water ice. The lunar South Pole contains permanently shadowed craters that haven't seen sunlight in billions of years. Temperatures there sit at negative 170 degrees Celsius, and tucked into those frozen shadows lies water ice. Lots of it. Water isn't just for drinking. Split it into hydrogen and oxygen, and you've got rocket fuel. You've got breathable air. You've got radiation shielding. You've got the foundation for agriculture. Every kilogram of water you can extract from lunar ice is a kilogram you don't have to haul up from Earth at $50,000 per pound. This completely changes the economics of space exploration. Right now, getting anything off Earth and onto the Moon costs about $10,000 per pound according to NASA. Want to send a 10-pound bag of rice? That's $100,000 just for transport. But if you can manufacture fuel on the Moon, suddenly Mars missions become feasible. Asteroid mining becomes profitable. The entire solar system opens up because you're not fighting Earth's gravity well every single time you want to go anywhere. The Moon becomes a gas station, a construction yard, a port of call for missions heading deeper into space. That's the prize both nations are chasing. And it's why the timeline matters so much. The technical challenges of actually building on the Moon make rocket engineering look simple by comparison. Start with the environment. The lunar surface exists in a vacuum so complete that it makes low Earth orbit look downright cozy. Surface atmospheric pressure measures roughly 3 × 10 to the negative 13 kilopascals. For reference, Mars has an atmospheric pressure of 0.7 kilopascals. The Moon essentially has no atmosphere whatsoever. Without an atmosphere, there's no protection from radiation. Astronauts on the lunar surface face radiation exposure an order of magnitude higher than what crew experience on the International Space Station, and several orders of magnitude beyond Earth's surface. That radiation comes from 2 sources: galactic cosmic radiation that's constant, and solar energetic particle events that can spike within hours. In August 1972, between the Apollo 16 and 17 missions, enormous solar flares erupted. Had astronauts been on the Moon during those events, they would have received potentially lethal radiation doses. We got lucky with timing. A permanent lunar base won't have the luxury of luck. Current studies show you need at least 1 foot of lunar regolith piled on top of habitats to provide meaningful radiation protection. Modern space shuttle hulls measured about 11 grams per square centimeter. The most heavily shielded areas of the ISS reach 15 grams per square centimeter. Storm shelters in proposed lunar colonies need to exceed 20 grams per square centimeter. That means construction techniques matter enormously. You can't just land some inflatable modules and call it home. Temperature presents another nightmare. The lunar surface swings from negative 170 degrees Celsius in shadowed regions to 110 degrees Celsius in direct sunlight. That's a 280-degree range. Materials expand and contract. Seals fail. Electronics malfunction. Every system needs to handle temperature extremes that would destroy most Earth-based equipment. Then there's the dust. Lunar regolith isn't like beach sand. It's been pulverized by billions of years of meteorite impacts into incredibly fine, incredibly sharp particles. This dust is electrostatically charged, so it clings to everything. It's abrasive enough to damage mechanisms and machinery. It gets into seals, bearings, joints. Apollo astronauts reported that it smelled like gunpowder and caused their spacesuits to degrade noticeably after just a few days. Building in 1/6 Earth's gravity creates its own problems. Construction techniques that work perfectly on Earth behave differently when everything weighs a fraction of what you expect. Structural loads change. Fluid dynamics change. Even simple tasks like pouring concrete require completely new approaches. And you're doing all this with limited equipment, limited spare parts, and a crew that can't just call for a replacement if something breaks. The nearest hardware store is 380,000 kilometers away with a 3-day transit time. NASA's solution involves sending massive cargo landers ahead of crewed missions. SpaceX's Starship cargo variant will transport a pressurized rover currently being developed by Japan's aerospace agency, no earlier than fiscal year 2032. Blue Origin's scheduled to deliver a lunar surface habitat no earlier than 2033. These cargo landers can land approximately 12 to 15 metric tons of heavy payload on the surface. The infrastructure plan is comprehensive: drones for aerial surveys, rovers for surface exploration and construction, habitats with life support systems, power infrastructure, both nuclear and solar, communications arrays, landing pads for human and cargo missions. The Artemis Base Camp will support missions of up to 2 months initially. Surface habitat modules will serve as the dwelling structures, humanity's first permanent homes away from Earth. But here's the fascinating part. We're not planning to build these structures the traditional way. The cost of launching construction materials from Earth is prohibitive. Even with reusable rockets driving down prices, you're still looking at thousands of dollars per kilogram. Building a base entirely from Earth-sourced materials would cost hundreds of billions. So engineers are developing something called In Situ Resource Utilization, ISRU, fancy term for use what's already there. The moon's surface is covered in regolith, that powdery abrasive dust that caused so many problems for Apollo missions. It's also a construction material. Mixed with the right binders or processed correctly, lunar regolith can be turned into building blocks, concrete, even metal. NASA's Kennedy Space Center and Sidus Space developed a 3D print head that uses regolith polymer mixtures as building material. The system can print structures layer by layer, creating habitats from the lunar surface itself. Early tests show these printed structures can achieve compressive strength suitable for construction. Other approaches use concentrated sunlight to sinter regolith into solid bricks. Solar furnaces can reach temperatures high enough to fuse lunar soil without any added materials. The resulting bricks aren't quite as strong as Earth concrete yet. Compressive strength currently sits below 5 megapascals, but researchers are improving the process rapidly. A newer technique combines lunar soil with polyaryl thirketone, a high-performance polymer. This hybrid approach requires less energy and produces more accurate results. Some printing systems now support both premix printing with binders as low as 4% by weight, and dry printing that achieves significantly higher flexural and bonding strength. The real breakthrough comes from microwave heating. Using a low-power microwave oven, just 250 watts, researchers extracted 55 to 67% of water from icy lunar regolith samples in less than 30 minutes. That's a game changer for water extraction operations, because getting water out of lunar ice isn't as simple as drilling and pumping. The ice is mixed into regolith in permanently shadowed craters where temperatures hover around -80 Celsius. You need to heat the soil enough to vaporize the ice, then capture the water vapor in cold traps. Several methods are in development. One involves installing reflective mirrors at crater edges to direct sunlight into shadowed regions, heating mining drills or tents where ice sublimates and gets collected. Another uses hollow auger drills that heat icy soil from within, vaporizing ice that's then captured. The microwave approach might prove most efficient, potentially reducing power requirements from 800 kilowatts to under 100 watts through grain sorting pre-processing. For a 6-person crew, water demands are substantial: 20 litres daily just for drinking, another 8.5 litres for rehydrating food. Water-efficient showerheads use 9 litres per minute. Total weekly consumption easily reaches 308 litres, which translates to 308 kilograms that don't have to be launched from Earth. But water's just the beginning. The vision for lunar ISRU extends far beyond keeping astronauts hydrated. Oxygen plants using molten regolith electrolysis could produce over 100 tons of oxygen monthly by the mid-2030s. The waste regolith from that process feeds into metal foundries that extract iron, aluminum, and magnesium. Those metals then supply autonomous robotic systems that construct roads, landing pads, and expanded habitats. The economic model follows distinct phases. The exploration age, from 2025 to 2030, features one-off government missions with limited infrastructure. The foundational age builds out transportation networks and pilot services for power and communications. The industrial age, targeted for 2035, scales up through commoditization. Multi-service hubs provide thermal management, power, and large-scale manufacturing. Finally, the jet age, where ISRU produces propellant depots enabling frequent, low-cost transport across the lunar surface. This phased approach mirrors how terrestrial infrastructure developed. First come the explorers, then the trail builders, then the railroads, then the cities. The moon's following the same pattern, just compressed into a couple decades instead of centuries. Cost estimates for all this vary wildly depending on assumptions. Conservative projections put a basic 4-person lunar base at $35 billion for development, plus $7.35 billion annually for operations. That annual cost assumes 2 crew rotations per year, Orion launches at $0.6 billion, corresponding heavy lift launches at $2 billion, and cargo deliveries totaling $3.75 billion. Other estimates run higher. One analysis suggests $36 billion to support 4 astronauts for a year, roughly $100 million per day. Yet NASA astrobiologist Chris McKay estimated the most basic possible base could start for as low as $10 billion. The range reflects uncertainty about how much infrastructure needs to come from Earth versus how much can be manufactured on site. An ambitious architecture proposal suggests creating a 1,000-person lunar colony for approximately $2 billion in development costs, $5 billion in transportation, and $1 billion annual support. That model assumes aggressive ISRU and mostly autonomous construction. Whether that's realistic remains to be seen, but it demonstrates how dramatically costs could drop if we crack the manufacturing challenge. Transportation expenses remain the biggest barrier. Current costs run about $10,000 per pound to lunar orbit. Sending humans and materials to the surface hits roughly $50,000 per pound. Even using lunar resources for construction, establishing a colony carries a baseline cost of several tens of billions. Reusable rockets are driving those numbers down. SpaceX's Starship aims to reduce launch costs by an order of magnitude or more. But even with massive cost reductions, building on the Moon represents one of the largest engineering investments in human history. The question isn't whether we can afford it. The question is whether we can afford not to. Because while NASA and its partners are planning methodically, China's moving fast. Their systematic approach through the Chang'e missions demonstrates serious intent. Landing on the far side proved technical capability. Returning samples showed operational maturity. The upcoming missions to scout ice and test construction technologies are explicitly designed to enable their 2030 crewed landing. And the International Lunar Research Station isn't just a concept. With 17 countries and 50 institutions committed, China's building a coalition that rivals or exceeds NASA's Artemis Accords partnerships. The timeline's aggressive. Some experts argue too aggressive. NASA's Space Launch System began development in 2011 with a mandated launch date of late 2016. Cost overruns and management issues delayed that by nearly 6 years. The Artemis program survived proposed budget cuts, showing it has staying power. But critics note that once human spaceflight programs reach a certain momentum, they tend to persist for decades, regardless of whether they're achieving objectives efficiently. Political and budgetary risks remain significant for both nations. Engineering challenges could push timelines right. A single major setback, a fatal accident, a launch failure during crewed operations could halt progress for years. Yet the momentum feels different this time. The Moon isn't just a destination anymore. It's a resource, a strategic position, a proving ground for technologies that'll take us to Mars and beyond. The nation that establishes the first permanent lunar presence doesn't just plant a flag. They write the rules for everything that comes after. And that's why the race is accelerating. Why timelines are compressing. Why billions in funding are flowing toward technologies that sound like science fiction, but are rapidly becoming engineering reality. The question isn't if we'll build cities on the Moon. It's who gets there first, and what they do once they arrive. Because the decisions made in the next few years will shape humanity's relationship with space for generations. But before anyone lives on the Moon permanently, we need to solve some problems that make rocket science look easy. The radiation challenge alone could derail the entire timeline if we don't get it right. Humanity's about to discover whether we're actually ready to become a multi-world species, or if we've been vastly underestimating what it takes to survive anywhere except the one planet that evolved us. Radiation doesn't care about your schedule. Between Apollo 16 and 17 in 1972, the Sun unleashed a series of massive solar flares during August 4th through 7th. Had astronauts been on the lunar surface, or in orbit during that window, they would have received potentially lethal doses. The timing was pure luck. A few weeks earlier or later, and the Apollo program might have ended with a very different kind of history. That's the reality waiting for anyone planning to live on the Moon. Radiation exposure there runs an order of magnitude higher than aboard the International Space Station, several orders higher than Earth's surface. And it's not just the baseline cosmic radiation streaming in from deep space. Solar energetic particle events can spike radiation levels on timescales of hours to days, with zero warning beyond whatever monitoring systems you've deployed. Earth's magnetic field and thick atmosphere shield us from most of this. The Moon has neither. Surface atmospheric pressure sits at roughly 3 × 10 to the negative 13th kilopascals. That's not thin air. That's effectively hard vacuum. Every cosmic ray, every solar particle, every bit of radiation that crosses the moon's orbital path hits the surface directly. How much protection do you need? Studies indicate you actually need up to 1 foot of regolith to meaningfully reduce radiation dose. Modern space shuttle hulls measured nearly 11 grams per square centimeter. The most heavily shielded areas of ISS reach 15 grams per square centimeter. Storm shelters in lunar colonies might need to exceed 20 grams per square centimeter to provide adequate protection during solar events. 1 meter of lunar soil piled on top of a habitat can substantially reduce exposure. But construction gets complicated fast when you're trying to support several feet of regolith overhead. The weight's not the issue in 1/6 gravity. The engineering challenge is building structures that can handle that load while maintaining pressurization, providing access points, and not collapsing if the soil shifts. Some researchers advocate for going underground entirely. Lava tubes offer natural protection. In 2024, scientists confirmed the first lunar lava tube in the Mare Tranquillitatis region. These formations can reach 1,260 feet wide, with rock ceilings 210 feet thick. Temperature inside stays around 63 degrees Fahrenheit. No wild swings from minus 170 degrees Celsius at night to plus 110 degrees Celsius during lunar day. No direct radiation exposure. Over 200 pits scattered across the moon might lead to similar underground spaces. Sounds ideal until you consider the logistics. You're building inside a cave with no natural light, limited access points, and the need to transport all construction materials through whatever entrance you find or create. Then there's the question of whether these tubes are actually stable over geological timescales, or whether the vibrations from heavy machinery might trigger collapses in areas that have sat undisturbed for billions of years. The alternative is surface construction with heavy shielding. NASA's approach involves regolith-based protection using indigenous materials. You pile lunar dirt onto structures designed to support the weight. Simple in concept. Brutally difficult in execution when you're working in vacuum suits with limited dexterity, using equipment that needs to function in temperature extremes and abrasive dust conditions. Lunar regolith isn't like beach sand. It's sharp, electrostatically charged, and gets into everything. During Apollo missions, it degraded seals, scratched visors, and caused equipment malfunctions. The stuff's essentially powdered glass mixed with tiny metal particles. Now imagine trying to pile tons of it precisely onto habitat structures without damaging seals, windows, or critical systems. Then there's the dust you kick up during construction. In Earth's atmosphere, dust settles quickly. On the Moon, particles launched by machinery or foot traffic follow ballistic trajectories. They can travel for kilometers before coming back down. And because there's no atmosphere to slow them, they hit with whatever velocity they achieved. High-speed regolith particles are basically microscopic bullets that can damage solar panels, sensors, and anything else exposed on the surface. Some proposed solutions involve sintering the regolith first, using concentrated solar energy or microwave systems to fuse the particles into solid bricks before construction. This approach reduces the dust problem and creates building materials with measurable structural properties. Early tests show it's technically feasible. Compressive strength of sintered regolith bricks currently runs below 5 megapascals, which might be too low for direct structural use without additional reinforcement. But the concept's improving rapidly. 3D printing offers another path. NASA's Kennedy Space Center developed a regolith polymer printing system that mixes about 90% lunar soil simulant with 10% bio-derived polymer. The resulting composite can be printed into various shapes and offers better flexibility than pure sintered regolith. Different research teams are testing everything from PLGA-based mixtures to polyarylethic blends, each optimizing for different properties. The real breakthrough would be printing structures that incorporate shielding during construction rather than adding it afterward. Imagine printing habitat walls that are already 1 meter thick, with the regolith integrated throughout the structure. No need to pile soil on top later. The protection's built in from the start. But this requires printing systems that can handle large-scale construction, operate reliably in lunar conditions, and use local materials with minimal processing. Water ice extraction faces similar engineering reality checks. There's water at the lunar poles, lots of it potentially. Most concentrated in permanently shadowed regions where temperatures stay below -160 degrees Celsius. That water's critical for everything from life support to rocket propellant production. But getting it out of frozen regolith isn't as simple as heating ice until it melts. One proposed method uses reflective mirrors at crater edges to redirect sunlight into shadowed areas. Sounds elegant until you start calculating mirror sizes needed to deliver meaningful heat to extraction sites located in permanent darkness. You're talking massive reflector arrays that need precise positioning and maintenance in one of the harshest environments in the solar system. Drill-based systems offer more direct approaches. Hollow augers bore into icy regolith, then heating elements vaporize the ice. The vapor gets captured by cold traps and condensed back into liquid water. Energy consumption varies wildly depending on ice concentration and initial temperature. Estimates range from 8.6 to 37.9 watt-hours per gram of water extracted. For a 6-person crew needing 308 liters per week, you're looking at substantial power requirements just for water production. Microwave heating shows promise for reducing energy costs. Researchers extracted 55 to 67% of water from frozen regolith samples using a 250-watt microwave oven in under 30 minutes. An innovative grain sorting process could potentially drop power needs from 800 kilowatts to under 100 watts by pre-separating ice-rich particles from dry regolith. That kind of efficiency improvement changes the entire architecture of mining operations and makes water extraction economically viable at smaller scales. But here's what nobody talks about enough. All these systems need to work autonomously for extended periods. You can't have astronauts babysitting water extraction equipment around the clock. The machinery needs to operate through lunar day and night cycles, handle equipment failures without immediate human intervention, and maintain production rates that meet consumption demands with enough surplus for emergencies and expansion. Same goes for power generation. Solar works during lunar day, which lasts about 14 Earth days. Then you've got 14 days of darkness. Battery storage for 2 weeks of operations. The mass alone makes that impractical for anything beyond minimal life support. Nuclear power solves the day-night problem, but brings its own complications. You're launching radioactive material, landing it safely, setting up a reactor on the lunar surface and maintaining it with limited on-site expertise. NASA's looking at both options. Solar array towers positioned at crater rims where they can catch sunlight for longer periods. Nuclear fission systems that can provide steady baseline power regardless of lighting conditions. The Artemis Base Camp design incorporates infrastructure for both, with distribution systems feeding habitats, rovers, and landing pads from multiple generation sources. Temperature swings add another layer of complexity. Surface temperatures range from -170 to +110 Celsius between lunar night and day. That's 280 degrees of variation. Every piece of equipment, every structural component, every seal and joint needs to handle that thermal cycling repeatedly without degrading. Expansion and contraction rates matter. Material selection becomes critical. Systems that work perfectly in Earth's relatively stable environment can fail catastrophically when subjected to lunar thermal extremes. The vacuum itself creates problems beyond radiation exposure. Heat dissipation works completely differently without atmosphere. On Earth, you can cool equipment through convection and conduction. In vacuum, you're limited to radiation and conductive contact with solid surfaces. Overheating becomes a serious concern for electronics, machinery, and even human habitats. Every watt of power consumed eventually turns into heat that needs to go somewhere. Life support systems face the same constraint. On ISS, excess heat gets radiated away through large external radiators. Lunar habitats need similar systems, but the radiators have to survive temperature extremes, micrometeorite impacts, and dust accumulation while maintaining efficiency through 2-week day-night cycles. And they can't be so large that they become impractical to transport and install. Then there's the question of what happens during solar particle events. You've built your habitat with adequate shielding for baseline cosmic radiation. Your crew's going about their daily routines. Then sensors detect a major solar flare heading your way. Particle arrival time might be anywhere from minutes to hours depending on the event's characteristics. Everyone needs to get to storm shelters immediately. Those shelters need to be accessible from anywhere in the base within minutes. They need life support for however long the event lasts, which could be days. They need enough space that crew members aren't crammed together in claustrophobic conditions for extended periods. And there need to be enough shelters that if one fails or becomes inaccessible, backup options exist. All of this adds mass, complexity, and cost to base design. Psychological factors matter more than most engineering discussions acknowledge. You're asking people to live in an environment that's actively trying to kill them, where going outside requires extensive preparation and carries real risk, where the view out the window is the same grey landscape in every direction, where communication with Earth has several second delays minimum, and where emergency evacuation isn't an option if something goes seriously wrong. Proposed designs address this by including communal spaces, individual gardens where crew members can grow plants of their choosing, and habitat layouts that maximize livable volume rather than just meeting minimum requirements. The goal isn't a space station on the moon with cramped modules. It's closer to an O'Neill colony concept, with large interior spaces that feel less like living in a submarine and more like living in an actual town. Whether that's achievable within mass and cost budgets remains to be seen. Some projections suggest housing up to 144 people using 3D printed modular components for adaptability. Others focus on smaller initial crews of 4 to 8 with expansion capability. The difference isn't just scale, it's philosophy. Do you start small and grow incrementally, or do you commit to large-scale infrastructure from the beginning with the expectation that it'll eventually be needed? China's International Lunar Research Station follows the first path. Basic model by 2035 at the South Pole. Extended model by 2050. Phased approach that allows learning from each stage before committing to the next. NASA's timeline compression pushes toward faster deployment of more capable infrastructure earlier. Both approaches carry risks. Go too slow and you lose momentum, political support, and competitive advantage. Go too fast and you might deploy systems that don't work properly, requiring expensive fixes or replacements. The Chang'e 7 and 8 missions launching between 2026 and 2028 will test water ice detection and construction technologies specifically to de-risk their 2030 crewed landing timeline. That's the smart play. Use robotic missions to validate concepts before risking human lives. NASA's doing similar work with commercial lunar payload services missions, but there's always tension between thorough testing and timeline pressure. Artemis 4 in 2028 represents NASA's first crewed surface mission in over 50 years. That's the mission everyone's watching. Because if something goes wrong there, if there's a major failure or loss of crew, the entire program could stall for years while investigations happen and safety measures get redesigned. The political will that's driving current timelines could evaporate overnight if Americans watch another space disaster unfold in real time. That's why radiation protection isn't just another engineering challenge to solve. It's the engineering challenge that could determine whether permanent lunar colonization happens in the 2030s or gets pushed back to the 2040s or beyond. Because unlike most other problems where you can design around failures or accept some level of risk, radiation exposure is cumulative, invisible, and potentially fatal. You either solve it properly or you don't send people to stay long term. There's no middle ground that's ethically defensible. The solution starts with understanding what radiation actually does to human tissue at the cellular level. High-energy particles slam into DNA molecules and break them. Your body has repair mechanisms for this. They work reasonably well at low doses, but there's a threshold where damage accumulates faster than it can be fixed. Cross that line long enough and you're looking at increased cancer risk, cardiovascular damage, central nervous system effects, and potential reproductive harm. The Apollo astronauts got lucky. Their missions lasted days, not months. They received doses well within acceptable limits despite having essentially zero shielding beyond their spacecraft hulls. But permanent settlement means cumulative exposure measured in years. That changes everything. 3 meters of lunar regolith provides adequate protection. That's the number that keeps appearing in shielding studies. Pile 3 meters of lunar soil on top of your habitat, and you've reduced radiation exposure to levels comparable to Earth's surface. Simple in concept, brutally difficult in execution. Because 3 meters of regolith weighs approximately 2 metric tons per square meter. A modest habitat with 100 square meters of roof area needs 200 metric tons of regolith moved and precisely placed. You can't just dump it randomly. The structure beneath has to support that load without collapsing, which means either bringing heavy support structures from Earth at enormous cost or building them on site using lunar materials. That's where 3D printing enters the picture. Not as a novelty or tech demonstration, as the only economically viable path forward. NASA's Kennedy Space Center developed a regolith polymer printing system that mixes approximately 90% lunar soil with 10% bio-derived polymer. The result is construction material that can be printed on site without shipping bulk materials from Earth. Early tests produced bricks with compressive strength around 5 megapascals. That's too weak for primary structural elements, but adequate for radiation shielding walls. More recent work using regolith polymer combinations with reduced binder content achieved 2.6 times higher flexural strength and 3.8 times better bonding strength. Those numbers matter because they determine whether printed structures can support their own mass, plus the overburden of protective regolith. The printing process itself has multiple competing approaches. Premix printing combines regolith and binder before extrusion. Simpler process but requires more binder material, which adds mass and cost. Dry printing deposits regolith powder in layers, then selectively applies binder only where needed. More complex equipment, but uses as little as 4% binder by weight. Each method trades different advantages against different constraints. China's Chang'e, 8 mission launching between 2026 and 2028, will test 3D printing feasibility in actual lunar conditions. That's smart validation before committing to full-scale construction. But printing technology alone doesn't solve the shielding problem. You still need to move regolith. Lots of it. Which brings us back to energy requirements and equipment mass. Moving 200 tons of material requires either many small loads with lightweight equipment or fewer large loads with heavy machinery. Lightweight equipment means more time and more operational complexity. Heavy machinery means higher upfront transportation costs, but faster construction once deployed. There's no obviously correct answer. It depends on mission architecture, timeline constraints, and risk tolerance. Some designers propose using natural lunar features instead of building everything from scratch. Lava tubes offer ready-made radiation protection. These underground cavities formed billions of years ago when molten lava flowed beneath the lunar surface. The roof cooled and solidified while lava continued flowing underneath, eventually draining away and leaving hollow tubes. Scientists confirmed the first lunar lava tube in 2024 in the Mare Tranquillitatis region. Measurements suggest some tubes reach 1,260 feet in width, with ceiling thickness exceeding 210 feet of solid rock. That's vastly more shielding than any constructed habitat could provide. Temperature inside lava tubes remains remarkably stable around 63 degrees Fahrenheit regardless of surface conditions. No more dealing with temperature swings from -170 degrees Celsius to +110 degrees Celsius. Radiation protection comes free, courtesy of geology. Micrometeorite impacts become irrelevant when you're under hundreds of feet of rock. The engineering challenge shifts from building radiation shelters to safely accessing and outfitting these existing structures. Over 200 pits on the lunar surface potentially connect to underground networks. Not all will be suitable for habitation, but finding even a few that work solves multiple problems simultaneously. The counter-argument centers on accessibility and expansion limits. Lava tubes exist where they exist. You can't choose their location based on proximity to water ice deposits or optimal solar exposure for power generation. Internal volume is fixed by geology. You can't easily expand when your population grows, and there's uncertainty about structural stability. These formations are billions of years old. Have they been weakened by thermal cycling or seismic events? Will they remain stable when you start installing equipment and pressurizing interior spaces? Nobody knows for certain until you actually try it. That uncertainty influences mission planning timelines. Do you commit early to a lava tube strategy, accepting location constraints and unknown structural risks? Or do you pursue surface construction with 3D printing, maintaining flexibility, but requiring more equipment and energy? NASA's current approach hedges by developing both capabilities. Commercial Lunar Payload Services missions are delivering scientific instruments to scout potential lava tube entrances. Simultaneously, regolith printing technology continues advancing. The first crewed surface missions will make final site selection decisions based on actual ground truth rather than orbital data and educated guesses. China's timeline follows similar logic with different emphasis. Their Chang'e 7 mission focuses specifically on water ice detection and resource mapping at the South Pole. Chang'e 8 tests construction technologies, including 3D printing. Both missions feed directly into site selection for their 2030 crewed landing. They're not rushing to plant a flag. They're systematically validating technologies needed for sustained presence. That methodical approach reduces risk, but requires patience. Political pressure for visible progress works against patient development, which is why both programs face constant tension between engineering realism and timeline ambition. The cost implications of different shielding strategies vary dramatically. Bringing 3 meters of shielding material from Earth for a 100 square meter habitat would require transporting 200 metric tons at current costs of roughly $50,000 per pound. That's £440,000 times $50,000. $22 billion for shielding alone. Completely unworkable. Using local regolith drops material costs to near zero, but requires excavation and placement equipment. A robotic system capable of moving 200 tons of regolith might mass 5 tons, including power systems and redundancy. Transporting 5 tons instead of 200 tons reduces launch costs by a factor of 40. Still expensive, but within the realm of feasibility. The energy cost of regolith excavation and placement adds another constraint. Moving 1 cubic meter of regolith requires lifting approximately 1,500 kilograms against 1/6 Earth gravity. That's 250 kilograms equivalent force. Doing this 200 times for 200 tons total means substantial energy expenditure even in reduced gravity. Solar power during lunar day can provide this energy, but construction might need to continue during the 2-week lunar night when solar panels produce nothing. Battery storage adds mass. Nuclear power adds political complications and regulatory hurdles. These aren't showstoppers, but they're real constraints that affect system design. Water extraction faces similar energy trade-offs. Heating frozen regolith to release water vapor requires significant thermal energy. Early estimates suggested 800 kilowatts of power for useful production rates. More recent grain sorting methods claim to reduce this to under 100 watts by concentrating ice-rich particles before heating. That's a dramatic improvement if it works at scale, but it adds mechanical complexity and another point of potential failure. 6 astronauts need roughly 308 liters of water weekly for drinking, cooking, and hygiene. That's 308 kilograms weekly, or 16,000 kilograms yearly. If you can extract water locally at 10% efficiency, you need to process 160,000 kilograms of regolith annually. Processing 160 tons of regolith per year for water, while simultaneously moving hundreds of tons for radiation shielding, means substantial surface operations. Multiple robotic systems working continuously, maintenance requirements, spare parts, inventory. Everything that can break eventually will break. Lunar dust gets into everything. It's electrostatically charged, microscopically sharp, and incredibly abrasive. Apollo astronauts reported significant equipment degradation from dust exposure during missions lasting just days. Long-term operations will face this problem continuously. Dust mitigation isn't a solved problem. It's an ongoing engineering challenge that affects every system with moving parts or exposed surfaces. And that brings us to something most discussions ignore: the compounding effect of multiple unsolved problems. Radiation shielding depends on regolith excavation, which requires reliable power, which depends on energy storage or nuclear systems, which require cooling, which requires radiators, which accumulate dust, which reduces efficiency, which increases power demand. It's not just solving individual problems, it's solving them in combination, while each solution potentially creates new complications for other systems. The same pattern appears everywhere. Water extraction depends on energy availability. Energy systems depend on thermal management. Thermal management depends on radiator efficiency. Radiator efficiency depends on dust mitigation. Dust mitigation depends on airlock design. Airlock design affects habitat pressurization. Habitat pressurization affects structural requirements. Structural requirements affect mass budgets. Mass budgets affect launch costs. Launch costs affect overall program affordability. Everything connects to everything else. This is why timeline estimates vary so wildly. Optimistic projections assume each technology works as designed and integrates smoothly with others. Pessimistic projections assume Murphy's Law applies recursively. Reality typically lands somewhere between, but closer to pessimistic. The Space Launch System started development in 2011 with mandated launch date of late 2016. It actually flew in 2022, 6 years late. Not because engineers were incompetent, because developing new spaceflight hardware is genuinely difficult and unexpected problems always emerge during testing. Artemis 4, scheduled for 2028, represents the first crewed landing attempt. That's 18 months away as of mid-2026. Hardware needs to be built, tested, integrated, and validated. Crew needs training time. Mission procedures need development and rehearsal. The timeline is aggressive but potentially achievable if nothing major goes wrong. History suggests something usually goes wrong, not necessarily catastrophically wrong, just wrong enough to require redesign or additional testing, which adds months to schedules. China's 2030 target faces identical pressures. Their hardware development is progressing, but they're attempting something they've never done before. Crewed landing requires different systems than robotic missions. Life support must be reliable. Abort modes must be thoroughly tested. Crew training takes years, not months. Saying you'll land astronauts by 2030 and actually doing it are different things. They might make it. they might slip to 2031 or 2032. Either way, the competitive pressure between nations creates urgency that didn't exist during previous space efforts. That urgency cuts both ways. It drives innovation and resource allocation. But it also creates incentive to accept higher risk or skip validation steps. The Columbia disaster happened partly because schedule pressure normalized accepting risks that should have triggered deeper investigation. Lunar missions operate under similar pressures now. Political capital invested in specific timelines creates resistance to delays, even when delays might be warranted by technical findings. This isn't unique to space programs. It's how large projects work when political oversight intersects with engineering reality. The question becomes whether radiation protection gets solved thoroughly or just adequately. Thorough solution means extensive testing of shielding effectiveness under actual solar particle events. Adequate solution means modeling-based confidence that proposed designs probably work. One approach takes longer but reduces crew risk. The other meets timelines but accepts uncertainty. Neither is obviously wrong. Different stakeholders weigh these trade-offs differently based on their priorities and risk tolerance. What's certain is that permanent lunar presence requires solving radiation protection before anyone stays long-term. You can send crews for short-duration missions with minimal shielding, just like Apollo. But asking people to live there for months or years without proper protection isn't ethically defensible, regardless of how badly you want to beat competitors or meet political deadlines. The physics doesn't care about timelines. High-energy particles keep hitting whatever's exposed. Biology keeps accumulating damage. Engineering must provide solutions that actually work, not just solutions that fit schedules. Water presents its own engineering puzzle. Humans need roughly 20 liters daily just for drinking. Add cooking, and you're at 28.5 liters per person per day. 6 crew members means 171 liters daily, over 1,200 liters weekly. That's 1,200 kilograms of mass if you're shipping it from Earth. Current launch costs run $10,000 per pound to low Earth orbit. Getting to lunar surface costs more. Call it $50,000 per pound conservatively. 1 kilogram equals 2.2 pounds. 1,200 kilograms equals 2,640 pounds weekly. Times 50,000 equals $132 million per week just for water transportation. Nearly 7 billion annually for water alone. Obviously, nobody's shipping water long term. The economics don't work. This is why lunar ice matters so much. Not because ice itself is particularly valuable, because extracting water locally eliminates the most expensive logistics problem in the entire architecture. Lunar poles contain water ice trapped in permanently shadowed craters. These regions never see sunlight. Temperatures stay below -170 Celsius. Ice deposited there billions of years ago remains frozen indefinitely. Estimates suggest millions of tons available, but distribution is patchy and concentrations vary widely. Extracting this ice requires solving several technical challenges simultaneously. First, you need power in regions that never see sun. Solar arrays don't work in permanent darkness. Nuclear reactors become necessary, which adds complexity and political complications. Then you need excavation equipment that functions in extreme cold and vacuum while handling abrasive lunar dust that wears down machinery faster than Earth conditions do. One proposed method uses reflective mirrors positioned at crater edges to redirect sunlight into shadowed regions. The concentrated light heats drilling equipment or enclosed tents where excavation occurs. Ice sublimates directly from solid to vapor without melting. You capture the vapor with cold traps, then condense it back to liquid or solid depending on storage requirements. Alternative approaches use microwave heating. Drill into icy regolith, then apply microwave energy to vaporize water in place. Research shows 250-watt microwave ovens can extract 55 to 67% of available water in under 30 minutes from frozen lunar soil simulants. Energy consumption ranges from 8.6 to 37.9 watt-hours per gram, depending on ice concentration and temperature. That energy requirement matters enormously. Thermal extraction methods initially required 800 kilowatts of power. Recent grain sorting innovations reduce that to under 100 watts for equivalent output. When you're operating on limited power budget far from Earth, that's the difference between feasible and impossible. But here's where reality intrudes on elegant plans. Laboratory demonstrations use lunar regolith simulants. Actual lunar ice sits under meters of dry regolith in terrain that's never been directly sampled. We have orbital data suggesting ice presence. We have reasonable confidence about general concentrations. We don't have ground truth about exact distributions or how easily it extracts under real conditions. Chang'e missions 7 and 8, scheduled for 2026 through 2028, will test some of these technologies. China's planning to scout water ice deposits and validate extraction techniques. Their timeline puts robotic resource utilization tests before crewed landings. Smart approach. Verify you can actually extract water reliably before committing humans to depending on that capability. NASA's taking similar path. Artemis missions focus initially on short-duration surface stays. Later missions will test ISRU equipment. By the time permanent bases get built, the technology should be proven at scale under actual lunar conditions. Should be. Optimistic word there. Three-dimensional printing offers another path towards self-sufficiency. Shipping construction materials from Earth costs prohibitively. But lunar regolith is everywhere. If you can print structures directly from local materials, you eliminate most transportation costs for base construction. Kennedy Space Center and Sidus Space developed regolith polymer printing systems. Mix 90% lunar soil simulant with 10% bio-derived polymer. Print structures layer by layer. Resulting composites show mechanical properties suitable for construction. Not as strong as Earth materials, but adequate for lunar applications when designed appropriately. Alternative methods use pure regolith without polymer binders. Concentrate sunlight with mirrors or lenses. Heat regolith to sintering temperature where particles fuse together. Build structures entirely from melted and resolidified lunar soil. Tests using xenon lamps as sunlight simulators successfully created first solar-printed bricks from regolith simulant. Compressive strength of those early bricks measured below 5 megapascals. Too weak for direct structural applications. But research continues improving sintering parameters and regolith processing. Hybrid approaches, mixing lunar soil with polymers like polyarylthecatone, show better strength while using less binder material than earlier formulations. The fundamental advantage of printing technology is you're not fighting lunar gravity well. Regolith is already there. No launch costs, no interplanetary transfer. Just excavate, process, and build. Energy becomes the main input rather than mass transportation. This is why landing pads and roads get prioritized in construction planning. Three-dimensional printed biomimetic structures can create stable surfaces for repeated landings without importing materials. Each landing on unprepared regolith kicks up dust that damages equipment and creates operational hazards. Prepared surfaces eliminate that problem while demonstrating printing technology at scales needed for habitat construction. Current estimates suggest landing infrastructure alone requires multiple cargo missions delivering construction equipment before first crews arrive. You need excavators to move regolith, processing equipment to prepare printing feedstock, the printers themselves, which are large industrial machines, not benchtop devices, power generation for all this activity, probably robotic systems to operate equipment remotely before human presence. This is another area where timelines get hazy. How long does it take to land all necessary equipment, then validate it works correctly? How many test prints before you trust the process enough to build crew habitats? What happens when equipment breaks down, as it inevitably will? You can't just order replacement parts from Earth and have them arrive next day. Supply chain logistics on the Moon means planning months or years ahead. Critical spares must be stockpiled in advance. Repair capabilities need development before things break. You probably want redundant systems for anything essential, all of which adds mass and cost to early missions. Then there's the question of where exactly you build. South Pole makes sense for water-ice access, but topography there is rough. Lots of craters and steep slopes. Finding suitable flat terrain for base construction while staying near permanently shadowed ice deposits constrains location options significantly. Lava tubes offer intriguing alternative. Scientists confirmed first lunar lava tube in 2024 in Mare Tranquillitatis region. These underground caverns reach 1,200 feet wide with ceilings over 200 feet thick. Natural radiation shielding. Stable temperatures around 63 Fahrenheit. Protection from micrometeorites and thermal extremes. Over 200 pits across the lunar surface might connect to similar underground networks. If accessible, these represent ideal locations for permanent bases. You avoid needing to pile 3 meters of regolith on top of surface structures. The rock overhead provides equivalent protection naturally. Construction becomes easier. Thermal management simplifies. Radiation exposure drops dramatically. But accessing lava tubes presents challenges. How do you get equipment and personnel down into pit that might be hundreds of feet deep? You need elevator systems or ramps. Internal volume must be mapped before construction planning. Structural stability needs assessment. Are these caves geologically stable, or do moonquakes pose collapse risks? Nobody knows yet because nobody's been inside one. Robotic missions could explore them first. Lower small rovers or drones into pits. Map interior geometry. Assess structural integrity. This becomes another prerequisite before committing to underground base architecture. The engineering decisions cascade endlessly. Surface base or underground, centralized or distributed. Modular habitats shipped from Earth or printed structures built in situ. Nuclear power or solar arrays with extensive battery storage. Each choice constrains subsequent decisions and affects overall timeline. China's International Lunar Research Station plans demonstrate this cascading complexity. Their architecture envisions basic model operational by 2035 at South Pole. Extended model by 2050 with expanded capabilities. That's a 25-year construction timeline for full implementation. 17 countries and 50-plus research institutions have joined the ILRS effort as of 2025. International cooperation theoretically accelerates development through shared resources and expertise, but coordination across multiple nations adds organizational overhead that can slow decision-making. NASA's approach focuses more narrowly on American-led development with selected international partners for specific capabilities. Japan provides pressurized rover, scheduled delivery no earlier than fiscal year 2032 via SpaceX Starship cargo lander. Blue Origin delivers surface habitat no earlier than 2033. These cargo landers can carry 12 to 15 metric tons of payload per flight. That tonnage limitation matters. Large cargo landers expand what's possible, but you still need multiple flights to deliver all necessary infrastructure. Each flight requires successful landing on unprepared or minimally prepared surface. Each landing risks damage to payload. Each mission adds time to overall deployment schedule. The Artemis Basecamp concept calls for surface habitat modules supporting missions up to 2 months duration, initial dwelling structure plus expandable components, power systems both nuclear and solar, pressurized rovers for mobility, landing sites for crew and cargo missions, communications infrastructure, life support systems. All this needs delivery and assembly before extended habitation becomes possible. Operating costs for even minimal 4-person base run $7.35 billion annually, according to NASA estimates. That's based on 2 4-person crew rotations yearly. Orion launches cost $600 million per year. Corresponding heavy lift launches $2 billion. Cargo requirements of 17.6 metric tons annually need 15 cargo flights at $3.75 billion. Those numbers assume everything works efficiently. No launch failures, no extended delays, no need for additional cargo beyond planned amounts. Real operations always exceed estimates. Equipment breaks, supplies run short, unplanned maintenance consumes resources. Actual costs will trend higher, not lower. Alternative estimates range wildly: $35 billion for initial development, $36 billion annually to support 4 astronauts works out to $100 million per day. NASA astrobiologist Chris McKay suggested $10 billion might cover most basic base possible, establishing full colony estimated between 250 and 500 billion total, depending on scope and timeline. These aren't just big numbers, they're program-killing numbers if not managed carefully. Political support for space exploration is fickle. Public enthusiasm wanes when costs escalate. Congressional appropriations depend on demonstrating value that justifies expense. Pure science rarely generates sufficient political will to sustain funding over decades. This is why economic rationales get emphasized. Lunar resources enable solar system expansion. Moon becomes stepping stone to Mars. Mining operations could eventually turn profit. Space industry creates high-tech jobs. Strategic competition with China demands American presence. Whether these justifications prove sufficient remains uncertain. History shows space programs survive when they align with broader national priorities. Apollo succeeded partly because Cold War competition made lunar landing symbolically important. International Space Station persisted through multiple administrations despite cost overruns because international partnerships created diplomatic commitments difficult to abandon. Lunar Base lacks obvious geopolitical symbolism of first moon landing. It's not a race with clear finish line. It's long-term commitment requiring sustained funding through multiple election cycles and changing political priorities. That's historically difficult to maintain absent compelling reason beyond science and exploration. The economic case remains speculative. Yes, lunar resources exist. Yes, they could theoretically support space industry. But profitable extraction requires technology that doesn't exist yet, plus market demand that hasn't materialized. Betting hundreds of billions on eventual commercial viability is optimistic at best. More realistic perspective acknowledges Lunar Base serves primarily as technology demonstrator and research platform. We learn how to live off-world, develop closed-loop life support, test resource extraction at scale, validate construction techniques, understand long-term health effects of reduced gravity and radiation exposure. That knowledge enables future expansion throughout solar system. But the knowledge itself doesn't generate revenue. It's investment in capability with payoff measured in decades, not quarters. Government programs can justify such timelines. Commercial ventures struggle with that calculus. This tension between exploration goals and economic sustainability will define how permanent lunar presence actually develops. Radiation shielding becomes the deciding factor between survivable habitat and death trap. Apollo astronauts spent only days on lunar surface. Future colonists need protection measured in years, not hours. Cosmic rays strike constantly. Solar particle events arrive unpredictably. Without Earth's magnetic field and atmosphere, the Moon sits exposed to radiation that would kill unprotected humans within days. Space station astronauts experience 10 times Earth's background radiation. Lunar surface dwellers face 10 times that. Here's what makes this particularly nasty. Radiation doesn't just increase cancer risk over decades. Acute exposure during solar storms can cause immediate radiation sickness. Apollo 16 and 17 had near miss in 1972. Massive solar flares erupted August 4th through 7th between missions. Had astronauts been on surface or in orbit, they'd have received potentially lethal doses. Modern space shuttle hulls measured 11 grams per square centimeter. International space stations' most protected areas reach 15. Storm shelters in lunar colonies need to exceed 20 grams per square centimeter just for emergency protection. Permanent living spaces require even more. 1 foot of regolith provides meaningful protection according to recent studies. That's about 30 centimeters of lunar dirt piled on habitat roofs. Sounds simple until you calculate weight. 3 meters of regolith, the commonly suggested depth, weighs enormous amounts. Supporting that mass requires structural engineering beyond anything attempted in space construction. Alternative approach uses subsurface construction. Scientists discovered first confirmed lava tube in Mare Tranquillitatis region during 2024. These volcanic tunnels stretch up to 1,260 feet wide, with ceilings 210 feet thick. Temperature stays steady at 63 degrees Fahrenheit. Over 200 lunar pits might connect to similar underground networks. Natural caves solve multiple problems simultaneously. Radiation shielding comes free from surrounding rock. Temperature extremes disappear. Micrometeorite impacts become non-issue. No need to transport shielding material or construct elaborate surface structures. But accessing caves creates new challenges. How do you build airlocks connecting surface to subsurface? What happens if structural failure seals exit? How do you evacuate during emergency? Cave-ins on Earth sometimes trap miners for weeks. Lunar rescue operations would be exponentially more complex. Water extraction technology needs to mature considerably before permanent habitation becomes viable. Lunar poles contain water ice trapped in permanently shadowed craters. Temperatures there hit -170°C. That's cold enough to preserve water for billions of years. Multiple extraction methods are under development. Drill-based systems use hollow augers to penetrate icy regolith, then apply heat to vaporize water. Vapor gets captured by cold traps and condensed into liquid. Microwave heating offers alternative approach. 250-watt microwave oven extracted 55 to 67% of water from frozen simulant in under 30 minutes during lab tests. Energy requirements vary wildly based on ice concentration and temperature. Range spans 8.6 to 37.9 watt-hours per gram. That difference matters enormously at scale. Crew of 6 needs 20 litres daily just for drinking. Add cooking, and you're at 28.5 litres per day. Water-efficient showers consume 9 litres per minute. Total weekly requirement easily exceeds 300 litres. 300 litres equals 300 kilograms. That's 660 pounds of water per week for 6 people. Annual requirement reaches 15.6 metric tons. If you're extracting at high end of energy range, that's 592 megawatt hours per year just for water production. That's roughly what 60 average American homes consume annually. Innovative grain sorting method potentially reduces 800 kilowatt thermal extraction down to under 100 watts. That tenfold improvement transforms entire mining operation economics. Suddenly, water extraction becomes feasible with solar arrays instead of requiring nuclear reactor. 3D printing with regolith represents another critical enabler. Transporting construction materials from Earth costs prohibitive amounts. Current estimates put space launch at $10,000 per pound. Sending building materials for even modest base would cost billions. In situ resource utilization solves this by using lunar dirt as construction material. NASA Kennedy Space Center developed Printhead using regolith polymer mixtures. 90% lunar simulant mixed with 10% bio-derived polymer creates printable composite material. Layer-by-layer construction builds walls directly from local resources. Sintering offers alternative approach. Concentrated sunlight melts regolith particles, which fuse together as they cool. Early tests produced bricks, but compressive strength below 5 megapascals proved too weak for structural applications. Ongoing research aims to improve bonding strength through better polymer mixtures and optimized printing parameters. Novel systems now support both premix and dry printing. Premix uses as little as 4% binder. Dry printing achieves 2.6 times higher flexural strength and 3.8 times better bonding strength. These improvements bring printed structures closer to viability for actual habitat construction. Environmental challenges extend beyond radiation and temperature. Lunar dust presents a serious problem, often underestimated. Apollo astronauts found regolith particles incredibly abrasive. Fine powder worked into suit joints, scratched visors, contaminated living spaces. One astronaut described it as smelling like gunpowder. Dust isn't just annoying, it's dangerous. Particles are sharp and jagged at microscopic level because no weathering processes exist to smooth them. Inhalation risks remain poorly understood, but likely significant. Dust also conducts static electricity, building up charges that could damage sensitive electronics. Vacuum environment means no air pressure. Habitats need pressurization to Earth normal levels. That creates massive structural stress. Every square meter of wall experiences 10 metric tons of outward force. Sealing becomes critical. Single puncture means rapid decompression. Multiple redundant systems and compartmentalization become mandatory design features. Temperature swings are brutal. Daytime surface temperatures reach 110 Celsius. Nighttime drops to negative 170. That 280-degree swing occurs over lunar day-night cycle lasting 29 Earth days. Thermal management systems must handle these extremes while maintaining comfortable interior temperatures. Psychological factors matter as much as engineering ones. Lunar environment contradicts everything human evolution adapted for. Confined spaces, recycled air, no weather, no seasons, limited social interaction, constant awareness that death waits outside thin walls. Antarctic research stations provide some analogues. Winter-over crews experience psychological stress from isolation and confinement. But Antarctica has breathable air outside, and evacuation remains possible if necessary. Moon offers neither safety valve. Design proposals increasingly emphasize livability, not just survivability. Concepts include communal gardens where crew members grow plants beyond what life support requires. Personal garden plots provide psychological connection to nature and social interaction opportunities. Main greenhouse handles food production, but individual spaces serve mental health needs. Spacious interiors help combat claustrophobia. Early concepts imagined connected modules similar to International Space Station. Cramped corridors and small volumes. Newer visions aim for O'Neill cylinder-style interiors. Large open volumes built from local materials. Pleasant spaces, not just functional boxes. One design proposes housing 144 people using modular 3D printed components. That's large enough for genuine community development. Small populations struggle with limited social dynamics. Larger groups enable diverse relationships and specialized roles. Timeline realism requires acknowledging historical patterns. NASA's Space Launch System began development in 2011, with government-mandated launch set for late 2016. Cost overruns and management issues delayed this nearly 6 years. Artemis program surviving budget cut proposals shows staying power. Once human spaceflight programs reach tipping point, they typically persist for decades. But persistence doesn't equal success on original timeline. Gateway Lunar Orbit Station was cancelled in March 2026. Hardware and systems get repurposed for expanded moon base plans. This pattern of revision and reprioritization will likely continue as technical challenges emerge and political priorities shift. China's timeline appears equally aggressive. 2 astronauts on Moon by 2030 using Mengzhou spacecraft and Lanyue lander. International Lunar Research Station basic model by 2035 at South Pole. Extended model by 2050. 17 countries and over 50 research institutions have joined this Chinese-led effort. Chang'e missions demonstrate systematic capability development. Chang'e 4 achieved first far-side soft landing in 2019. Chang'e 5 returned samples in 2020. Chang'e 7 and 8, launching between 2026 and 2028, will scout water ice and test construction technologies. This methodical approach builds confidence in Chinese ability to meet stated goals. competition between American and Chinese programs creates interesting dynamics. Political pressure to maintain leadership could accelerate funding and development, but it might also encourage corner-cutting and premature deployment. Space exploration rewards patience and thoroughness. Race mentality sometimes conflicts with those virtues. Critical technologies must mature before permanent habitation becomes realistic. In situ resource utilization tops the list. Without local material use, every kilogram needs transport from Earth at enormous cost. Successful ISRU transforms economics entirely. Power generation remains fundamental challenge. Solar arrays work during 14-day lunar day, but provide nothing during 2-week night. Battery storage for that duration requires massive capacity. Nuclear reactors offer continuous power, but present their own challenges. Reactor transport, waste heat management, radiation safety, political acceptance of nuclear systems. Water extraction must scale from laboratory demonstrations to industrial production. Gap between proof of concept and reliable operations always proves larger than initially expected. Equipment fails. Unexpected problems emerge. Efficiency in controlled conditions doesn't match field performance. Life support systems need orders of magnitude more reliability than anything currently operating. International Space Station gets regular resupply from Earth. Lunar base, particularly during early phases, will have limited backup options. System failure that's inconvenient on ISS could be fatal on Moon. Communications infrastructure requires development. Direct Earth-Moon contact works only for near-side. Far-side missions need relay satellites. Network architecture must provide reliable coverage for both robotic operations and human safety. Medical capabilities present unique challenge. What level of healthcare can Lunar Base provide? Routine problems can become emergencies without proper facilities. Surgical capability requires specialized equipment and trained personnel. Medical evacuation to Earth takes days minimum. Some emergencies don't allow that delay. Psychological support systems need development. How do you provide mental health care in isolated, confined environment? What screening identifies candidates likely to thrive versus those who will struggle? How do you handle interpersonal conflicts when people can't leave? All these challenges are solvable. None violate physical laws, but solving them requires time, testing, iteration, and resources. Aggressive timelines often underestimate this reality. Statements about landing astronauts before specific political terms end reveal more about political pressure than engineering assessment. Realistic perspective acknowledges lunar base development as multi-decade endeavor spanning multiple technology generations. Initial bases will be small research outposts dependent on Earth support. Gradual expansion of capabilities and population comes only as systems prove reliable and costs decrease. The vision of true self-sufficient colony remains distant. That requires not just surviving on Moon, but thriving there. Growing food, manufacturing equipment, processing materials, building new structures, eventually having children and raising families. Each step multiplies complexity exponentially, but even modest permanent presence represents profound achievement. Humans living continuously off Earth for first time in history, learning whether long-term reduced gravity proves compatible with human health, developing closed-loop life support at scale, establishing industrial processes using extraterrestrial resources. That knowledge enables everything that follows. Economic realities ultimately determine whether lunar bases remain government research stations or evolve into permanent settlements. Launch costs create the primary barrier. Current price sits at roughly $10,000 per pound to low Earth orbit. Getting that same pound to lunar surface costs significantly more. Simple arithmetic reveals the challenge. 6 astronauts need 308 liters of water weekly just for drinking, cooking, and basic hygiene. That's 308 kilograms. At $50,000 per pound to lunar surface, you're looking at $34 million per week just for water. These numbers explain why in situ resource utilization isn't optional luxury, but absolute necessity. Without local resource extraction, lunar base becomes bottomless money pit. Every consumable shipped from Earth, every spare part, every tool. The logistics chain stretches 250,000 miles with months-long lead times and astronomical costs. Water extraction demonstrates the transformation ISRU enables. Permanently shadowed craters at lunar poles contain billions of tons of water ice. Multiple extraction approaches show promise. Drill-based systems use hollow augers to penetrate frozen regolith, then apply heat to vaporize ice. Microwave methods prove surprisingly efficient. Researchers extracted 60% of water from simulated lunar soil using just 250-watt microwave oven. Less power than typical kitchen appliance. Energy requirements vary dramatically based on ice concentration and temperature. Range spans from roughly 9 to 38 watt-hours per gram depending on conditions. Innovative grain sorting techniques could reduce power needs from 800 kilowatts down to under 100 watts. That's not incremental improvement. That's complete transformation of operational architecture. But here's what nobody mentions in promotional videos. Gap between laboratory demonstration and reliable field operation always exceeds predictions. Equipment fails in unexpected ways. Lunar dust proves more abrasive than anticipated. Thermal cycling between 2-week day and 2-week night stresses materials beyond Earth experience. Components that worked perfectly in testing develop problems during extended operation. 3-dimensional printing with lunar regolith represents another critical technology. Bringing construction materials from Earth makes no economic sense. Local fabrication using abundant lunar soil changes everything. NASA and partners have developed multiple approaches. Regolith polymer mixtures create surprisingly strong composites. 90% lunar soil simulant combined with 10% bio-derived polymer produces versatile elastic materials suitable for various applications. Sintering approaches use concentrated sunlight, or lasers, to fuse regolith particles without binders. Initial results show feasibility, but compressive strength below 5 megapascals may prove inadequate for direct structural applications. Research continues on hybrid methods. Low binder powder printing achieves flexural and bonding strength improvements of 2.6 and 3.8 times respectively, compared to conventional approaches. These technologies sound impressive in papers and presentations. Reality involves years of incremental refinement. First-generation equipment operates at fraction of theoretical efficiency. Second generation fixes obvious problems, but reveals new issues. Third generation finally approaches reliability needed for mission-critical applications. This pattern repeats throughout engineering history. Lunar construction won't prove exception. Power generation timeline illustrates the gap between concept and deployment. Solar arrays work brilliantly during 14-day lunar day. Panels convert sunlight to electricity with proven technology. But then comes 14-day night. Batteries capable of storing 2 weeks of power for entire base represent massive mass and cost. Alternative approaches like solar towers at crater rims, where sunlight hits nearly continuously, help but don't eliminate storage requirements. Nuclear reactors provide continuous power regardless of day-night cycle. Small modular reactors designed for space applications could supply tens or hundreds of kilowatts continuously for years. But nuclear systems bring unique challenges. Reactor must survive launch vibration and landing impact. Waste heat in vacuum environment requires large radiator arrays. Radiation safety demands careful positioning relative to habitats. Political acceptance of launching nuclear materials remains uncertain in some nations. Hybrid approaches combining solar, nuclear, and storage probably make most sense. Redundancy increases reliability. Multiple power sources mean single failure doesn't catastrophically disable entire base, but complexity increases exponentially with each additional system. More equipment to transport, more interfaces to integrate, more potential failure modes to analyze. Habitat construction reveals similar complexity layers. Early concepts envisioned inflatable modules transported from Earth. These work for initial outposts, but don't scale to permanent settlements. 3 meters of regolith shielding provides radiation protection, but creates structural and operational challenges. How do you pile 3 meters of loose soil on inflatable structure without damaging it? How do you prevent slow leaks when micrometeorite inevitably punctures outer layers? Rigid structures built from sintered or printed regolith offer better long-term solution. Natural features like lava tubes provide ready-made radiation shielding. Scientists confirmed first lunar lava tube in 2024. These structures span up to 1,260 feet wide with ceiling thickness exceeding 200 feet. Interior temperature remains stable around 63 degrees Fahrenheit, perfect for base construction. Over 200 pits on lunar surface might lead to accessible lava tubes, but utilizing these natural features requires extensive robotic reconnaissance. Which tubes are structurally sound? Which contain accessible flat floor areas? How do you seal entrances to maintain pressure? What about emergency egress if primary entrance becomes blocked? Each question spawns engineering studies. Each study reveals additional complications. Timeline projections consistently underestimate time required to address these layers of complexity. Apollo programs succeeded through massive focused effort and virtually unlimited budget relative to technical scope. Modern lunar base development lacks both unified focus and blank check funding. Medical infrastructure requirements illustrate another dimension of challenge. International Space Station maintains limited medical capability. Most serious issues require evacuation to Earth within hours. Lunar base can't offer that option. Journey back to Earth takes days minimum. Many medical emergencies don't allow that delay. What level of surgical capability does lunar base need? Appendicitis happens. Broken bones occur. Dental emergencies arise. How many medical specialists must base support? What equipment is essential versus nice to have? Training non-medical personnel for emergency response helps but has limits. Would you want fellow engineer with 2 weeks medical training performing your emergency surgery? Telemedicine assists, but speed of light delay makes real-time guidance impossible. Round-trip communication lag to Earth exceeds 2 seconds. Surgeon on Earth watching video feed experiences delay that prevents direct procedure control. Pharmaceutical supply presents related challenge. Medications have shelf life. Radiation exposure may degrade certain compounds faster than on Earth. Refrigeration for temperature-sensitive medications consumes power. Comprehensive pharmacy for potential medical needs involves hundreds of different drugs. Each requires storage space, inventory tracking, expiration date monitoring. Psychological support infrastructure remains perhaps least understood requirement. Antarctic research stations provide some analogues. Small groups isolated in harsh environment for extended periods. Interpersonal conflicts emerge. Depression affects some individuals. Substance abuse occasionally occurs despite screening. But Antarctic stations allow evacuation when situations deteriorate. Rescue flights can reach most locations within days. Lunar Base offers no such option during many mission phases. Crew selection becomes critical. What psychological profiles predict successful adaptation? How do you screen for resilience under isolation stress? What's optimal crew size to maintain social dynamics while minimizing resource demands? Too small and social isolation intensifies. Too large and interpersonal conflicts become statistically inevitable. Habitat design influences psychological well-being. Cramped quarters like early spacecraft concepts create oppressive environment. More spacious designs using local construction materials offer better long-term livability. Private sleeping quarters, common areas for socializing, exercise spaces, greenhouses serving both food production and psychological benefit of tending plants, windows or high-quality displays showing Earth and space views. These human factors don't appear in technical specifications, but determine mission success or failure. History shows that technical capability alone doesn't guarantee achievement. Human elements matter equally. Lunar Base, where crew suffers deteriorating mental health, won't accomplish scientific objectives regardless of perfect hardware performance. Communication architecture requires careful planning. Direct Earth-Moon contact works for near-side locations. Far-side missions need relay satellites. Constellation of communication satellites around Moon enables continuous coverage but represents additional infrastructure cost. Each satellite requires launch, orbital insertion, station-keeping fuel, replacement cycle as systems age. Bandwidth requirements grow with mission complexity. Early missions transmit limited telemetry and occasional video. Permanent base with multiple simultaneous activities needs substantially higher data rates. High-definition video from multiple locations. Scientific instrument data streams. Internet connectivity for crew morale. Remote operation of robotic systems. Telemedicine consultations. All competing for available bandwidth. Latency affects operations differently than bandwidth. 2-second round-trip light delay seems minor but prevents real-time conversations. Discussions become exchange of monologues rather than flowing dialogue. Remote operation of equipment requires autonomous systems for immediate response with human oversight, for strategic decisions, rather than tactical control. Legal and governance frameworks remain underdeveloped. Outer Space Treaty establishes basic principles, but predates permanent settlement concepts. Who has jurisdiction over Lunar Base? What laws apply? How are disputes resolved? If multiple nations operate separate bases, do they function as embassies with sovereign territory, or does different framework apply? Resource extraction rights create particular ambiguity. treaty prohibits national appropriation of celestial bodies but permits use of space resources. What constitutes appropriation versus use? If entity extracts water ice and processes it into rocket fuel, does that constitute ownership? Can they sell that fuel to others? These questions need answers before major commercial investment occurs. Environmental protection considerations emerge as bases expand. Moon lacks biosphere to damage, but preserving scientifically valuable sites matters. Apollo landing sites represent historical artifacts. Permanently shadowed craters contain pristine records of early solar system. How do you balance resource utilization against preservation? Who decides which areas remain off-limits to development? International cooperation offers benefits but introduces complications. Shared costs enable more ambitious projects. Diverse expertise improves problem solving. Political risk distribution provides stability, but coordination overhead grows with number of partners. Technical decisions require consensus building. Different national priorities sometimes conflict. Schedule delays in one country's contribution affect entire program. China's International Lunar Research Station already includes 17 countries and over 50 research institutions. This broad participation demonstrates appeal of collaborative approach, but also highlights coordination challenges as partnership expands. NASA's Artemis program maintains smaller core partnership with bilateral agreements for specific contributions. Each model has advantages depending on programmatic goals. Economic sustainability requires eventual transition from government funding to self-supporting activities. What products or services can lunar base provide that justify costs? Tourism represents obvious possibility, but probably not primary economic driver initially. Launch costs must decrease substantially before lunar tourism becomes accessible to anyone beyond ultra-wealthy individuals. Propellant production for deep space missions shows more near-term promise. Water electrolysis produces hydrogen and oxygen. These make effective rocket propellants. Refueling spacecraft in lunar orbit, rather than launching full fuel load from Earth, significantly reduces mission costs for Mars and beyond. Lunar Propellant Depot could service commercial, scientific, and national security space missions. Scientific research provides another economic justification, though often overlooked. Radio astronomy from lunar far side escapes Earth's radio interference. Unique geology provides insights into planetary formation. Low gravity enables experiments impossible on Earth. But translating scientific value into economic return remains challenging. Research rarely generates immediate profit despite long-term technological benefits. Manufacturing specialty materials in lunar environment might eventually justify economics. Certain crystal structures grow better in low gravity. Specialized alloys benefit from vacuum processing. These niche applications won't support entire base, but could contribute to economic viability as technology matures. The path forward requires accepting that lunar colonization spans generations, not election cycles. Modest permanent presence within next few decades seems achievable. True self-sufficient settlement remains distant goal. Each intermediate step provides knowledge enabling subsequent advances. Rushing process to meet arbitrary political deadlines risks catastrophic failure, setting programs back decades. Patient, persistent effort better serves long-term success. Technical advancement follows learning curves, not straight lines. Achieving water extraction efficiency, improvements from 800 kilowatts to 100 watts didn't happen through a single breakthrough. Dozens of incremental refinements accumulated over years of testing. The same pattern applies across all critical systems. Initial 3D printed structures using lunar regolith showed compressive strength below 5 megapascals. Current techniques achieve significantly higher performance through refined binder ratios and printing parameters. But even current methods need further optimization before supporting multi-story pressurized habitats. Power generation exemplifies infrastructure interdependencies. Solar arrays work during 14-day lunar day, but require massive battery banks for equally long night. Nuclear reactors provide constant power, but require extensive radiation shielding and cooling systems. Both options need years of development before deployment. Meanwhile, habitat life support systems, water processing equipment, and construction machinery all demand reliable power from day one. Chicken and egg problems abound throughout base planning. Transportation infrastructure presents another foundational requirement. Landing pads constructed from sintered regolith prevent rocket exhaust from creating dangerous debris clouds during descent and ascent. Roads between facilities enable efficient cargo movement and emergency response. But building this infrastructure requires construction equipment already on site, which means early missions must bring equipment from Earth, then use that equipment to build infrastructure enabling local resource utilization. Only after that foundation exists can self-sufficiency begin. Communication systems create less obvious but equally critical dependency. Real-time control of robots from Earth proves impractical due to signal delay averaging 2.6 seconds round trip. Autonomous systems must handle immediate decisions independently. But complex problem-solving still benefits from human oversight and expertise. This requires base personnel capable of operating and maintaining sophisticated equipment, which means extensive training programs and backup systems for when things inevitably fail. Medical capabilities represent another essential consideration often underestimated in early planning. ISS maintains telemedicine connection to Earth-based specialists for diagnosis and treatment guidance. Lunar-based personnel face similar isolation, but with day-long evacuation times instead of hours. Emergency medical situations require on-site capability for surgery, trauma care, dental work, and mental health support. Small crew size means cross-training multiple people in overlapping specialties. Medical equipment must function reliably in lunar gravity and radiation environment. Pharmaceutical supplies need careful inventory management with long supply chain delays. Food production systems demonstrate sustainability challenges. Hydroponics and aeroponics enable growing fresh vegetables, supplementing packaged rations. But complete nutritional self-sufficiency requires far more complex agricultural systems than simple salad greens. Protein sources present particular difficulty. Raising livestock seems impractical at small scale. Fish farming shows more promise but needs substantial infrastructure. Plant-based proteins work but require crop diversity and processing equipment. Most realistic approach involves hybrid system combining local production of some foods with continued Earth resupply of others. Complete food independence likely requires base population exceeding several hundred people. Waste management proves more complicated than simply recycling water and air. Human waste contains nutrients valuable for agriculture, but also potential pathogens requiring careful treatment. Equipment eventually wears out, generating metal scrap, plastics, electronics waste. Some materials get recycled. Others lack practical reprocessing methods at small scale. Accumulating waste storage becomes increasingly problematic over years. Long-term sustainability requires closing these loops, but solutions depend on technologies still under development. Social dynamics within isolated confined populations create challenges beyond technical systems. Antarctic research stations provide useful analog for understanding psychological stresses of lunar base life. Limited privacy, restricted communication with loved ones, inability to leave, repetitive routines, and high-stress work environments all contribute to mental health challenges. Crew selection processes screen for psychological resilience, but cannot eliminate human friction entirely. Base design incorporating private spaces, recreational facilities, and nature elements helps but doesn't fully substitute for Earth's environment. Cultural differences between international crew members introduce another dimension of complexity. Language barriers, different work styles, varying social norms, and conflicting expectations all require careful navigation. Training programs emphasizing cross-cultural competence help, but real situations inevitably create unexpected tensions. Mission success depends on crew cohesion despite these differences, which means investing heavily in team building and conflict resolution before anyone leaves Earth. Family considerations eventually emerge as bases transition from rotational crews to permanent settlement. Do personnel bring spouses and children? If so, when? What educational and recreational facilities do children need? How do you handle medical situations during pregnancy or childhood illnesses? These questions seem distant concerns during initial base establishment, but become central issues as permanent presence develops. Different cultural attitudes about family separation influence how various nations approach these decisions. Governance structures within base community require careful consideration. Traditional hierarchical military-style command works for short missions with clear objectives. Longer-term settlements need more participatory decision-making, engaging residents in choices affecting daily life. But democratic processes can prove cumbersome during emergencies, requiring immediate action. Balancing efficiency against autonomy remains an ongoing challenge. Legal frameworks must address this before significant conflicts arise. Property rights concerning improved land and constructed facilities need clarification. If crew member spends months building greenhouse, does that create ownership claim? Can personnel starting private business using base resources? What happens when someone wants to leave but has invested years in local projects? These scenarios seem hypothetical until they actually occur. Then lack of clear rules creates serious problems. Developing governance frameworks addressing these issues takes time and careful thought, best done before problems manifest. Scientific research priorities versus commercial development create potential tensions. Researchers want pristine sites preserved for study. Companies want access to resources for extraction. Tourism operators want iconic locations for visitors. Military interests seek strategic positioning. Balancing these competing demands requires regulatory framework that doesn't yet exist. International negotiations move slowly. Meanwhile, first movers on lunar surface establish de facto control over desirable locations. This creates resentment and potential conflict among latecomers. Environmental protection on apparently lifeless world seems paradoxical, but actually matters significantly. Apollo landing sites represent irreplaceable historical artifacts documenting human achievement. Permanently shadowed craters contain water ice records spanning billions of years. These scientific resources get destroyed by careless development. Some areas deserve protection from industrial activity. But how do you enforce restrictions in environment lacking clear jurisdictional authority? These debates need resolution before major development proceeds. Technology transfer between lunar base and Earth applications offers frequently overlooked benefit. Closed-loop life support systems developed for space-find applications in sustainable building design. Water recycling technologies help address terrestrial scarcity. Remote medical diagnostics improve rural healthcare. Autonomous construction equipment enables work in hazardous environments. These spin-off benefits justify some program costs, even if lunar base itself never achieves economic self-sufficiency. Educational inspiration represents another intangible but valuable return on investment. Apollo program inspired generation of scientists and engineers. Modern lunar base could provide similar motivation for students pursuing STEM careers. Live feeds showing daily life and work on Moon make space exploration tangible rather than abstract. This cultural impact justifies portion of public funding even skeptics acknowledge. Climate change mitigation through space-based solar power remains speculative, but potentially transformative application. Collecting solar energy in space avoids atmospheric absorption and nighttime interruption. Beaming power to Earth via microwave transmission could provide clean baseload electricity. Lunar resources enable constructing enormous solar arrays impractical to launch from Earth. This vision requires decades of development, but lunar base provides essential stepping stone toward realization. Asteroid mining for platinum group metals and other rare materials eventually becomes economically viable as Earth reserves deplete. Lunar base serves as logical staging point for missions to near-Earth asteroids. Lower gravity makes launching mining equipment easier than from Earth. Propellant production from lunar water supports these missions, processing facilities on Moon handle returning ore. This creates economic ecosystem benefiting lunar settlement while providing valuable materials to Earth. Long-term survival of human species provides ultimate philosophical justification for becoming multiplanetary civilization. Earth faces existential risks from asteroid impacts, supervolcano eruptions, nuclear war, pandemics, or unforeseen catastrophes. Lunar colony represents first step toward ensuring humanity survives regardless of what happens to homeworld. This perspective frames short-term costs as insurance premium protecting humanity's future. Mars colonization remains ultimate goal for many space advocates, but Moon provides essential proving ground for technologies and techniques needed on Red Planet. Lower gravity than Mars, but higher than space stations. Closer proximity enables rapid problem-solving iteration, impossible with Mars's months-long communication delays. Lessons learned establishing lunar base directly inform Mars mission planning. Skipping Moon and going straight to Mars increases risk of catastrophic failures. Private sector involvement accelerates development while introducing profit motives, sometimes conflicting with scientific or exploratory goals. SpaceX, Blue Origin, and other companies bring innovation and efficiency often lacking in government programs. But corporate interests prioritize returns over pure research. Finding balance between public and private participation shapes program trajectory significantly. Too much government control stifles innovation. Too much privatization risks neglecting non-commercial objectives. Optimal model probably involves partnership, recognizing strengths of both sectors. Realistic timeline assessment suggests modest permanent presence within next 2 decades, followed by gradual expansion rather than rapid colonization. China aims for crewed landing by 2030. NASA targets similar timeframe, though with less aggressive schedule. Both programs face technical and budgetary challenges, potentially causing delays. But even accounting for setbacks, some form of permanent lunar presence before 2040 seems achievable given current momentum. First permanent residents will live in conditions resembling Antarctic research stations more than Earth cities. Small crews rotating every few months initially, gradually extending mission durations as systems prove reliable, eventually transitioning to personnel staying years rather than months. Population growth measured in dozens, not hundreds, during 2030s and 2040s. Only after that foundation solidifies does serious expansion toward true colony become feasible. Century from now, lunar settlement might house thousands, supporting thriving economy based on propellant production, scientific research, manufacturing, and Earth observation, or might remain small research outposts similar to Antarctic bases if economic case never materializes. Predicting which future unfolds requires humility about uncertainties ahead. But attempting the endeavor itself pushes boundaries of human capability regardless of ultimate outcome. Your role in this story depends on choices made today. Supporting space exploration through advocacy and education helps maintain political will funding these programs. Pursuing STEM careers provides technical expertise enabling breakthroughs. Even simply paying attention sends message to decision makers that public cares about humanity's future beyond Earth. The moon waits patiently for us to return. Question isn't whether we can build colony there, it's whether we will. The infrastructure exists in blueprints and prototypes. The knowledge base grows daily through research and testing. Political will fluctuates but persists across administrations and borders. Money flows in billions, though not yet hundreds of billions. What's missing isn't capability, but commitment to multi-generational timeline. Space enthusiasts want dramatic announcements. Politicians want ribbon-cutting ceremonies before next election. Engineers know reality involves decades of unglamorous incremental progress. Gap between these perspectives creates constant tension in program planning. Managing expectations while maintaining momentum defines the real challenge. Consider what permanent actually means in this context. Not self-sufficient colony independent of Earth. That remains distant aspiration requiring technological advances we can barely envision. Permanent means continuous human presence. Someone always there even as individuals rotate home. Like Antarctic stations where personnel change but facility persists. That modest goal is achievable, probably within 2 decades given current trajectories, but requires accepting limitations of early bases, small populations, heavy Earth dependence for supplies, limited economic productivity, years of operational experience needed before expansion makes sense. The alternative is rushing toward ambitious targets for political reasons, then watching programs collapse when reality intrudes. Apollo succeeded partly because clear finish line existed. Plant flag, return safely, declare victory. Permanent settlement has no comparable endpoint. Success gets measured in sustained operations over years, becoming decades, becoming generations. Water extraction technology matures through testing, not pronouncements. Radiation shielding proves adequate through long-term exposure data, not simulations alone. Three-dimensional printing achieves structural reliability through iteration, not first attempts. Each capability requires patient development, resisting pressure for premature deployment. Lava tubes offer intriguing possibility, but need robotic exploration before committing base architecture to underground locations. Natural radiation protection and thermal stability provide enormous advantages. But accessing caves safely, verifying structural integrity, and building inside constrained spaces introduce complications offsetting those benefits. Surface construction using regolith shielding represents better understood approach, even if less elegant. Medical infrastructure determines maximum safe crew size more than habitat volume. Cannot responsibly station more people than can receive adequate care during emergencies. That calculation involves surgical capability, pharmaceutical inventory, trained personnel, and evacuation options. Building comprehensive medical facility on Moon costs enormous amounts and requires specialized equipment. Early bases will necessarily operate with limited capabilities, accepting higher risk. Psychological support systems need equal priority despite receiving less attention than hardware. Mental health challenges in isolated, confined environments are documented and predictable. Screening helps but cannot eliminate problems entirely. Base design incorporating private spaces, recreational facilities, nature elements, and communication infrastructure addresses some needs. But ultimately, small population size limits social dynamics in ways no design can fully overcome. Economic sustainability remains biggest question mark. Propellant production for deep space missions shows clearest path to revenue generation. But market size depends on future Mars missions and commercial space activity that hasn't materialized yet. Betting base viability on optimistic projections about space economy growth in 2030s and 2040s involves substantial risk. Scientific research justifies government funding, but rarely generates profit. Radio astronomy from far side enables observations impossible on Earth. Unique geology provides insights into planetary formation. Low-gravity experiments advance materials science. These contributions have value but don't pay bills directly. Long-term knowledge benefits often fail to convince budget committees focused on near-term returns. Manufacturing specialty materials in lunar environment might eventually contribute to economic viability, but requires decades of development before production scales reach commercial relevance. Crystal growth, vacuum metallurgy, and other niche applications show promise as technical demonstrations. Whether they evolve into profitable industries remains speculative. Tourism gets mentioned frequently as potential revenue source. Reality involves limited market at prices only ultra-wealthy can afford. Even with dramatically reduced launch costs, lunar tourism serves a tiny fraction of population. Comparison to Antarctic tourism proves instructive. Roughly 50,000 visitors annually despite being far more accessible and affordable than moon trips. Lunar tourism might eventually support some base operations, but won't drive colonization. The honest assessment acknowledges we're building lunar base primarily for strategic and exploratory reasons, not economic ones. China's expanding space capabilities create competitive pressure. Desire to maintain technological leadership motivates American investment. Scientific curiosity drives research community support. long-term vision of multiplanetary civilization inspires public enthusiasm. These factors sustain programs even without clear profit motive. That's actually fine. Government funding enabled transcontinental railroads, interstate highways, internet development, and countless other infrastructure investments that seemed economically questionable initially, but proved transformative long-term. Lunar Base fits that pattern. Initial costs exceed obvious benefits, but capabilities developed enable future applications we can't fully anticipate. The mistake would be promising economic returns that won't materialize, then watching political support evaporate when reality disappoints. Better to acknowledge BASE serves strategic, scientific, and inspirational purposes, while remaining open to commercial opportunities that may emerge unexpectedly. Under-promise and over-deliver beats the reverse. Timeline compression for political reasons poses greatest risk to long-term success. Rushing crews to surface before systems prove reliable invites disaster. Single major failure could halt programs for years, just as Challenger and Columbia grounded shuttle fleet. Patient development seems boring compared to dramatic announcements, but serves mission objectives better. China's systematic approach through Chang'e missions demonstrates value of incremental capability building. Each mission validates technologies needed for subsequent steps. Chang'e 4 proved far-side landing. Chang'e 5 demonstrated sample return. Chang'e 7 and 8 will test water extraction and construction before risking human lives. That methodology reduces risk even if it frustrates people wanting faster progress. NASA's Artemis program faces pressure to demonstrate results quickly. Administrator pledging boots on Moon before specific political term ends reveals priorities emphasizing speed over thoroughness. That creates tension with engineering culture valuing methodical testing and validation. Managing this tension determines whether programs achieve sustainable presence or spectacular failures. International cooperation offers benefits but introduces coordination challenges. China's International Lunar Research Station includes 17 countries and 50+ institutions. Broad participation shares costs and expertise, but also requires consensus building slowing decision processes. NASA's smaller partnership with bilateral agreements maintains flexibility while still enabling collaboration. Neither model is obviously superior. Each trades different advantages against different constraints. Legal frameworks governing lunar activities need development before major commercial investments occur. Outer Space Treaty prohibits national appropriation but permits resource use. That distinction grows murky when entities extract water ice, process it into propellant, then sell to customers. Does that constitute appropriation? How are disputes resolved? What environmental protections apply? These questions need answers not decades from now, but within next few years as capabilities mature. The path forward requires accepting that lunar colonization is marathon, not sprint. Modest permanent presence achievable within 2 decades. Gradual expansion following that as technologies mature and experience accumulates. True self-sufficient settlement probably remains 2060s or 2070s goal, requiring advances in manufacturing, agriculture, and closed-loop systems we're only beginning to develop. That timeline frustrates people wanting dramatic transformation in their lifetimes, but matches historical patterns for major infrastructure development. Transcontinental Railroad took decades from concept to completion. Interstate highway system required 20 years of construction. Internet evolved over 30 years, from military network to commercial platform. Colonizing another world naturally requires similar timeframes. Your grandchildren might vacation on Moon. Your great-grandchildren might be born there. That's aspirational timeline, assuming steady progress without major setbacks. More conservative projection pushes those milestones further. But trajectory is clear, even if exact timing remains uncertain. Humanity is becoming multiplanetary species. Question isn't if, but how quickly, and what that means for civilization. The decision facing current generation is whether to commit resources enabling this transition or defer to future generations. Deferring seems easier in short term. Money spent on lunar base could address terrestrial problems, but some investments transcend immediate returns. Some achievements justify costs through expanding what's possible for humanity. Becoming multiplanetary civilization fits that category. Critics argue money would serve better exploring solar system with robots rather than risking humans on Moon. Valid perspective deserving consideration. Robotic missions provide exceptional science at fraction of human mission costs. But humans enable capabilities robots cannot match. Adaptability in unexpected situations, real-time problem solving, inspiration that resonates with public in ways robot achievements don't. The debate between human and robotic exploration will continue. Probably both approaches serve complementary purposes. Robots scout and characterize. Humans follow, establishing permanent presence, enabling long-term research and development. Neither approach alone optimizes outcomes. Balanced portfolio investing in both maximizes returns across different timescales. Climate change arguments cut both directions. Some say we should fix Earth before attempting Moon colonization. Others argue becoming multiplanetary provides insurance against terrestrial catastrophes. Both perspectives hold merit. Reality is, we need to do both, not choose between them. Humanity possesses resources and capability addressing climate change while pursuing space exploration. False choice between them serves neither goal. Near-term focus should emphasize technology validation over symbolic achievements. Test water extraction at scale. Prove 3D printing produces reliable structures. Demonstrate closed-loop life support for extended durations. Validate radiation protection adequacy. These unglamorous milestones matter more than planting flags or holding press conferences. Once technologies work reliably, human presence follows naturally. The Moon waits exactly as it has for billions of years, indifferent to human timelines and political pressures. Our choice is when we return permanently and what we accomplish once we stay. That choice shapes not just space exploration, but human civilization's trajectory for centuries ahead. Whether we become multiplanetary species or remain confined to single world, whether we expand capabilities and knowledge or accept current limitations as permanent. This moment resembles countless historical inflection points where civilizations chose between expansion and consolidation. Vikings sailing to Iceland and Greenland, Polynesians navigating to remote Pacific islands, Europeans crossing Atlantic to Americas. Each expansion involved risk and cost. Each fundamentally altered human civilization. Lunar colonization continues that pattern on grander scale. The infrastructure pieces are moving into position. Technology development accelerates. International competition drives investment. Political will fluctuates, but persists. Economic models remain uncertain, but opportunities exist. Most importantly, Human curiosity and ambition push boundaries despite obstacles. That combination historically proves sufficient for achieving seemingly impossible goals. So, when can we build colony on Moon? Modest, permanent presence within 2 decades seems achievable. Growing settlement through 2040s and 2050s as capabilities mature. True self-sufficient colony probably requires another generation beyond that. But the journey begins with decisions made today about priorities and resource allocation, about accepting multi-generational timelines over instant gratification, about investing in humanity's future beyond Earth, even when returns seem distant and uncertain. The Moon is waiting. The question is whether we're ready to stay.